Let's take a look at a few more of the area between the curve questions. And for the next 3 examples in this homework video guide, the problems will focus around finding the area between the curves when you need to integrate along the y-axis. Okay, so let's take a look at some of the equations that are given to us. I have y equals to the square root of x minus 1. And I've gone already and I've kind of pretty much graphed the results using decimals already. So here is the square root of x minus 1. So I will just highlight some of the key points again. If I have y equals to x, that's this linear line right here. And then I'm given y equals to 0, which is this horizontal line right there. So that's y equals to 0. And finally, I also have y equals to 2, which is another horizontal line right there. So that's y equals to 2. And the area that's being generated or enclosed by all 4 of these curves is this yellow region right here. So I need to write an integral expression to find that particular area. Now, when you're given 2 horizontal lines and the area is trapped between those 2 lines, that's a very good indicator that you should integrate this along the y-axis and not the x-axis. Okay, so when we're setting up our integral, just like the previous problems, you can definitely start off by saying the integral from a to b, and you could say the top minus the bottom, and you're going to integrate that along perhaps dx, for example. But since we're going to integrate this along the y-axis, I'm going to change the dx to dy. And the language that we use for top and bottom when we're integrating along the y-axis, we can slightly change those words as well. So let me show you how we can set up our integrals here. So I will draw a line, a black line over here at the very edge here. So maybe I'll start over here on the far left, and I will draw a horizontal line right through that area there, the yellow area. And this dot right here, you know, that's kind of like the top function, and this right here is like the bottom function. Right, so instead of using top and bottom, since I'm drawing a horizontal line this time, another term that we could use to represent top and bottom is outer and inner, which are pretty much the same thing as like top minus bottom. But since I'm drawing a horizontal line, I will go ahead and just say outer minus the inner function. Okay, and what is the outer function? So if I take a look at this outer function, it's basically this the square root function. So that's going to be the square root of x minus 1, and then minus, and then what is the inner function? Well, the inner function is just this blue line, right? So this inner function is the equation y equals to x. So I will write an x over here, and I will definitely do some substituting a little bit later. And let's take a look at the upper and lower bounds. Well, since I'm integrating along the y-axis, I need to take a look at the lower bound, which is y equals to 0, and my upper bound is 2. So I'm integrating this from 0 to 2. Okay, so let me just erase that, and let me just kind of play with this next little line here. Okay, so that's looking a little messy here, so let me just rewrite that as from 0 to 2. Okay, so this is a general setup here, and another thing that you might recognize is that if I have a dy here, I can see that my upper and lower bounds are in terms of y, because I'm going from the bottom all the way to a height of 2. However, if I take a look at the variables inside, the variables are different. The variables are in terms of x, and I need the variables in terms of y. So what we're going to do is we're going to make another substitution step here. If I take a look at this function right here, I know that y equals to the square root of x minus 1. And what I'm going to do here is I'm going to try to isolate for x here so that I can get y, so I can get everything in terms of y. So I can square both sides, and if I do that, I get y squared equals to x minus 1. And then I can move the 1 to the other side. So that's going to be y squared plus 1. So this is the function that is going to replace my my outer function now. So let me just erase all this. And instead of writing the square root of x minus 1, I will now write y squared plus 1. Okay, so we're writing this, we're isolating for x, and we're making sure that the variable is in terms of y now, which is good. All right, let's go ahead and now change this variable over here, which is the inner function. Well, I know the original equation is y equals to x, so I can just interchange x with y. So I can erase this now, and that will simply just be y. All right, so as you can see, if I just compare everything on the inside here, everything is now in terms of y. So now we're ready to find the antiderivative and evaluate this using the fundamental theorem of calculus. All right, so here we go. The antiderivative of y squared plus 1 is y cubed divided by 3 plus y minus, and then the antiderivative of y is y squared divided by 2. And then after that, I can put this in a square bracket, going from 0 to 2. The good part here is that the lower bound is 0, so I can just focus my attention on the upper bound and plug that in for all the y values. So that's going to be 2 to the power of 3 divided by 3 plus 2 minus 2 to the power of 2 divided by 2. Whoops, I had 4 there, but it's a power of 2 there. Okay, and that's going to be 8 divided by 3 plus 2 minus, well, this is going to be 4, and 4 divided by 2 is going to be 2. So then these guys will cancel off, and your final answer is 8 divided by 3. Okay, let's move on to the next question now. Okay, so for my next problem, I have the equations y equals to e to the x, which is this graph right here. That's going to be y equals to e to the x. And then I also have this square root function, y equals to the square root of x, and that's going to be highlighted by this graph right here. And then I have these horizontal lines. I have y equals to 1 here, so that's just a horizontal line right there in green. So it's y equals to 1, and I also have this other horizontal function, y equals to e, which is a horizontal function right there, and e is a constant as well. And the area that's being enclosed by all 4 of these graphs is this yellow region right here. So it's very similar to the previous problem. We're just given different functions and different constants here. Because you're bounded by these 2 horizontal lines, the yellow region is bounded by this upper bound of y equals to e and this lower bound of y equals to 1, it's best to integrate this along the y-axis. Okay, so if you're going to integrate along the y-axis, it's going from a to b, and I will now use the word outer minus inner. That's pretty much my own made-up language here, just to kind of help me set up the expressions there. And if I'm integrating along the y-axis, dy here, we should definitely go to the far left here. This is where I'm going to start. And just draw a horizontal line right through the enclosed area. And then you can see that this dot right here, this is the outer function. And this dot right here is going to be the inner function. Okay, so what is the outer function? Well, the outer function is the blue line, and the blue line has the equation y equals to root x. So let's go ahead and plug in root x right away, and then minus that from the inner function. Now the inner function is touching the red line, and the equation of the red line is e to the x. So let's write down e to the x right there, and then close that off, dy. And what are my lower and upper bounds? Well, my upper and lower bounds are just e and 1, those 2 horizontal lines. Okay, so I can go from 1 to e. And let me just erase all that. And then let's take a look at this integral expression here, because once you have this set up, you just have to make sure that all the variables you have to make sure that everything on the inside has a variable y and not x. So you do have to do a little bit more work here to make sure that your integral expression is set up correctly. Now to do that, just take a look at the original equation. This equation is y equals to root x. And what you're going to do is you're going to isolate for the x variable. All right, so let's go ahead and solve for x here, so I can square both sides. And if I do that, I get y squared equals to x. Okay, so this is now the function that's going to go inside my integral expression now. So I'm going to erase all this, and I'm going to have y squared. Okay. And then over here I have the original function for this guy was y equals to e to the x, and I need to isolate for x, so I can ln both sides. If I ln both sides, I get ln y over here on the left hand side, and this x just comes in the front, so it's going to be x times ln e, and ln e is just 1, so I can just erase that. So that means x equals to ln y. After that, I can erase this, and I can replace the inner function with just ln y. And after that, if I take a look at all my variables inside here, I notice that everything is now in terms of y. So now I'm ready to actually integrate. I'm actually ready to integrate this function now. Before you start this problem, the question did give a little hint. The question did give you the integral of ln x dx. You actually have to use integration by parts to get the final answer here, but the problem just pretty much gives you what the antiderivative of ln x is, which is x times ln x minus x plus c. So we're going to use that little fact there to kind of help us find the antiderivative. Once again, the question actually gives us this as a hint, but you would need integration by parts to get that answer. Okay, let's get back to the original problem now here. So the antiderivative of y squared is y cubed divided by 3 minus, and then since I have the variable y here, I can just replace all the x's over here with y's. So that's going to be y ln y minus y, and I'll put that in a bracket. And then all of this is going to be in a square bracket, and my lower bound is 1 and my upper bound is e. Okay, now we're going to spend a little bit of time evaluating this using the fundamental theorem of calculus. So the upper bound starts first. So let's go ahead and plug in the upper bound there. So that's going to be e to the power of 3 divided by 3 minus e ln e. And then if I actually distribute that, that's going to be a plus. And if I substitute the e now, that's going to be plus e. So I can put all that in a bracket. That's kind of like your capital F of B minus your F of A. And for that, let me just erase this, and we're going to go ahead now and evaluate our lower bound in for all my y's. And if I do that, I would get 1 to the power of 3 divided by 3 minus 1 times ln 1, and then plus, remember that minus sign makes that a plus, so plus 1, and then close off that bracket. And that right there is my fundamental theorem of calculus. And after that, we just need to do our best to simplify this to our best ability here. Okay, so let's go ahead and try. Let's go ahead and try to simplify this. I can't simplify this first term, so that's going to be e cubed divided by 3 minus. Well, ln e is just going to be 1, so 1 times e is just e, so minus e, and then I have a plus e there. So I guess those guys will cancel out eventually. And then I have a minus, minus what? I have a minus 1/3. Then I have a plus. Well, ln of 1 is going to be 0, so that's going to be just 0. And then a minus and a positive is going to give me minus 1 at the very end there. Okay, so if I go ahead and simplify this a little bit more, the e's will cancel off. And if I have negative 1/3 minus 1, that's going to be negative 4/3. Now those are done. And then I just have my first term, which is e cubed divided by 3. So that is my final answer for that problem. Okay, let's move on to the last question in this homework video guide. Okay, in this final question here, I have a few more of these functions here. I have y equals to e to the power negative x, so that's this red line right here. So that's going to be y equals to e to the power negative x. And then I have this function right here, y equals to 1 over x, and I just have parts of the graph of that right here. So that's the first part. The other graph, if I actually graph this properly, the other part of that is down there. But I don't think we need that part for this particular problem. So y equals to 1 over x. And then we have these two horizontal lines here. I have y equals to 1, so that's this horizontal line here. And once again, once you have those horizontal lines, that's a very good indicator that you should be integrating along the y-axis. And then here's y equals to e. So this is going to be my upper bound, and this is going to be my lower bound, just like the previous two questions. And the area that's being enclosed by all four of these graphs is this yellow region right here. Okay, and let's go ahead and let's figure out our integral expression here. So the integral expression is the integral from a to b. And since I'm integrating along the y-axis, the language I'll use is outer minus inner times dy. Okay, let's go ahead and figure out our boundaries first. This is my lower bound and this is my upper bound. So I'm being enclosed between this vertical distance here. So let me just change my a and b to reflect that right away. That's going to be 1 and all the way up to e. Okay, and then let's go ahead and find my outer function. Just like the previous problems, you might want to put a dot at the far left-hand side and say start, and you just draw a horizontal line right through the yellow area there. And I can definitely see at this point right here, this is my outer function. So my outer function is blue, and what's the equation of the blue line? Well, it's 1 over x. So let's go ahead and put in 1 over x minus my inner function, and my inner function is this dot right here, which is the red function, and the red function has the equation y equals to e to the power negative x. Alright, so let me put that in for my inner function here in red. So that's going to be e to the power negative x. And then I will go ahead and I will close the brackets here and multiply that with dy, and my integral is going from 1 to e. Okay, so the last thing that we have to do here before we can start finding the antiderivative is we have to remind ourselves that if we're integrating with respect to y, that means all the variables here have to be in terms of, you need to have the y variables there. So we need to go ahead and isolate or change those expressions. Okay, so what is the original equation for this? Well, the original equation for that is 1 over x. And if I go ahead and interchange the y and the x, that's going to give me x equals to 1 over y. Okay, so this will now be my new outer function. That's going to be 1 over y. And for this part right here, the original equation was y equals to e to the power negative x. And I need to go ahead and isolate for the x variable, so I can ln both sides. If I ln both sides, I just get ln y on the left-hand side. And this negative x, that just comes in the front, so that's going to be negative x. And then basically this ln e, I mean, if you want to write it down, you can, but ln e is just 1, so ln e just kind of disappears. After that, you might want to just transfer this minus sign to the left-hand side, so that's going to be negative ln y. So this right here is my new function after I've isolated for the x variable, and then everything is in terms of y now. Okay, so let's go ahead and replace that. Let me erase all the steps here and erase that. I'll get out a blue marker here. So bracket negative ln y. Okay, so as you can see, everything is now in terms of y, so now I can find the antiderivative. Let me just create another line here and simplify the inside. So that's going to be 1 over y, and that's going to be now plus ln y. Before we start finding the antiderivative here, you may recall that for ln y, the integral for ln y dy, that was kind of given to us in the previous problem as well, and we kind of need this to kind of finish off the problem. The antiderivative of ln y dy is going to be y times ln y, and then minus y. And then you can also have a plus c there if you like. Okay, so once again, if you want to find the antiderivative of that, you need to use integration by parts, but the questions in the homework actually give you this as a hint, so we can definitely use that to finish off this problem here. Okay, let's go ahead and find the antiderivative now. The antiderivative of 1 over y is ln y, so ln absolute value y, plus the antiderivative of that, which we already kind of wrote in the top right hand corner there, that's going to be y times ln y minus y. And then all of this is now being bounded between 1 and e. And now we need to find our final answer by using the fundamental theorem of calculus. All right, so let's start with the upper bound. E goes in for all the y's, so there's quite a bit of y's there. So let's do this very slowly. This is going to be ln e plus e times ln e minus e. So that's the first that's the upper bound minus the lower bound. Let me erase all that. And let me highlight the lower bound now. So that will now replace all the y's. And if I do that, that's going to be ln of 1 plus 1 times ln 1 minus 1. And then close the bracket off. Okay, over here, this is going to be ln e is just 1, and that ln e is also just 1. So that's going to be 1 plus, well, e times 1 is just e, and then minus, actually no, I made a mistake here. This is a y there. I forgot to plug in the e for that, so that's going to be minus e. So I'm just sorry about that. So I will erase that, and that's going to be e. So small mistake there, I do apologize for that. And then let's go ahead and keep simplifying this. I know that ln of 1 is going to be 0, so that's going to be 0 plus, and that's also going to be 0, and then minus 1. Almost done here. I know that this e and that e will cancel off, giving just a 1 there, minus, and then I guess I have a minus 1 there. So that's going to be 1 plus 1 equals to 2. So my final answer there is 2, and make sure that you do have the e value there, which is something I forgot when I was substituting my values. Okay, so I hope that helps with the integral setup there. Just make sure that you are very careful when you're finding the antiderivative and plugging in your upper and lower bounds. It's very easy to make a simple mistake.